Hello and welcome to the Visualizing GC with JavaFX talk. This is a very slightly different title from the one that was actually advertised, which was Visualizing the JVM Runtime. The reason for this is because when we started this project, as you'll see in a minute, we thought we were going to write 4 or maybe 5 of these applications and just step you through a whole raft of these things to visualize all of the runtime. However, we started with GC, and GC kind of got away from us, as you'll see. It started out life as a very simple application, but as we got into writing the project, we realized that there was a lot of sophistication we could bring to it, and we were having so much fun with it that we decided we'd just do one big application instead. So hence the slightly different title. So for people that don't know me, I'm Ben Evans.
I'm James Goff.
And how do we know each other? What's the basis of this talk? Well, we do a bunch of things together. We helped run the London Java community. We've both worked in banks over the years. We both like beer.
Yeah, definitely. And how I actually met Ben was at my first job interview when he was technically grilling me across the table. And we then met up 2 years later when I recognised him from my nightmares in a bar. Oh, I was actually after our own conference at the London Java community. So that's how we got to know each other and started working on a few toy projects.
Okay, so this story about where this application and where this project came from starts, as with so many things, we are British after all, it starts with beer and pubs. So we were up late at night and we were just talking about the JVM, what makes it special and why we think it's a good platform, and some debate and some back and forth, which is, I guess, kind of typical for when developers get together late at night and beer has been drunk. And really what we came to is that there's an important design principle that underlies the JVM, which people don't often talk about or recognize. And that's the whole purpose of the JVM, what makes it unique, is the extent to which it uses runtime information to influence the management of JVM processes themselves. So if you have C or C++, which is a statically compiled ahead of time language, which doesn't do any kind of dynamic compilation, you're actually throwing away an awful lot of information. All you have is the type of information that's available at runtime, and you don't have a lot of good numbers as to how the code's actually going to be used, because you just have no idea about the runtime. And Java and the JVM are designed with a very different principle in mind. And part of this comes out of a lot of the software engineering that was done in the 1980s and the 1990s, where people realized that if you analyze the runtime behavior of software, there was all sorts of strange and unexpected empirical things that you found out about the runtime behavior of software. And so things like the young generational hypothesis for garbage collection, things like monomorphic dispatch in terms of which methods get dispatched, or inlining, or all of these other techniques, which are just not there at compile time. You only see them if you analyze runtime information. So the Java platform really is an attempt to harness that dynamic information and to make the runtime more efficient. So we thought about that, and we thought about the fact that in many cases there aren't a lot of good teaching tools, and a lot of Java developers grow up without really having been introduced to that as an idea, and in need of some tools to help illustrate this. And we do a lot of speaking and a lot of teaching, so it seemed like a very natural fit. So yeah, GC just started to acquire more and more complexity the more we got into it. So we decided to just do this one. The code's all available on GitHub, so that's my username there, and that's the project head. So if you want to go and grab that and go and find it, then feel free. We'll step through some of the code a bit later on, but if you want to play along at home and want to start right now, then you can totally do that. Yeah, so when we first started, we originally made a Flash demo. And that was basically because we weren't sure we were actually really building. We knew we wanted to build some teaching tools, and one of our other friends, Anna, actually was a very accomplished Flash designer. So she actually built us a Flash version. So let's just take a quick look at that. Okay. So for people that know the Java memory model, this should be working in Chrome, perhaps? Okay, well that's the first, probably and hopefully only sacrifice to the demo gods. Let's try this again in Safari, shall we? I swear this was working in Chrome this morning. Maybe it's just disabled something. There we go. Wow. Sigh. Okay, let's try this in Firefox. Firefox is my reserve backup browser. There we go. There we go. Try this again. There we go. Can everyone see that okay? So here we have a Flash demo which represents main memory. We have an object graph which collapses into a single block, and this is a very simplified view of memory. And now you can see that we've got a whole bunch of different allocating threads that are allocating on different TLABs. Hands up if you know what a TLAB is in the context of memory allocation. Oh, only one person. Okay. So let me tell you a little bit about this while the demo is running. So a TLAB is one of those horrible acronyms which actually has two separate meanings. It can mean a translation look-aside buffer from the point of view of dealing with memory and kernel paging, or it can mean a thread local allocation buffer. And that's the context that we use it in when we're talking about the Java memory model. Okay. Because there's a secret about Java memory management that you may not know, and that is that if you're familiar with C and C++ programming, hands up if you've done any C or C++ programming. Okay, so how do you get a new object or a new block of memory in C or C++? Well, you use the malloc system call. And that means you're making a call into kernel space. But if you've ever sat and looked at the CPU utilization of a Java process while it's doing heavy allocation, you may not see any kernel traffic at all, any kernel space or context switches to kernel. The reason for that is because the Java virtual machine actually allocates its entire memory space up front. So it reserves a big block of memory, which is the whole area, and then it just manages its pointers in user space without ever touching kernel space. So what that means is you could divide your memory area up into chunks. You could give a small piece of the memory area to each thread that needed to allocate. And then allocation for that thread would be incredibly fast, because all you have to do is just bump the pointer by a few bytes. So that's just an offset operation. So that means that in the Eden space, and hands up if you know terms like Eden and survivor space for memory management. Good, pretty much everyone. Excellent. So in Eden, that means that you can allocate in order 1, because all you're doing is bumping the pointer. Yeah, occasionally you might need to go and get an extra TLAB, but that's basically all you have to do. And then what happens is when memory fills up, well, you garbage collect it. You take all the dead objects, you swap over the survivor space, and both Eden and the existing survivor space that you are currently using are now completely free. So let's just watch that one more time. I promise there'll be some JavaFX in a sec. Build the object graph, start allocating. Notice how all the other spaces start off empty. And then when this collects, you'll see that those objects are transferred over into one of the survivor spaces. Okay. When this refills again, that will swap down to the second space. And this is basically how Java deals with the young generational hypothesis, which is the runtime observation that most objects die young. And what you need to do is you need to size your pools such that you want to do a lot of young, cheap collections, and basically try to make as many of those objects die, while at the same time making the trade-off that anything which is really going to stick around for a long period of time, you don't want to be constantly flipping it backwards and forwards between spaces. Okay, so that's the JavaFX. That's the Flash demo. Okay, let's come back here. And thanks, Diana, for that one. So, why convert this to JavaFX? Well, as a teaching tool, it's pretty good. We sat there. I hope a couple of people in the audience learned something, and it was a good talking point. It was a nice graphical aid. But there were a whole bunch of problems with it. First and biggest is that it's quite dumb. It's just an animation. It just loops. It goes through the same thing each time. It can't easily be changed because we're not Flash developers. We don't. Even if we had the source for it, we probably couldn't modify it very easily. But mostly is that it has no real awareness of what's going on. So we started to think, could we do something a bit better? What would happen if we started to think about this and think, well, JavaFX is a UI technology. We've had a bit of play with it. Seems quite nice. What could we do? Well, how about if we just redevelop the whole application as a Java and JavaFX app? Now that's interesting, because we know how to write Java. And that means that we could actually do some things like actually model the memory. We could actually have like a real version of the GC algorithms. Wouldn't that be interesting? So that's what we did. And these are some of the design goals that we had. So we wanted to actually model GC. We wanted to have a proper domain model. So in the code that we're going to show you, we have actual memory blocks. We have actual areas and real memory pools which model the exact ones that are inside the Java virtual machine. We have objects which model actual threads allocating data and actually running computations. That was great. So we started with that. And then we started to get a bit ahead of ourselves, and this is where the complexity started to snowball, and we started to realize that this was probably the only one we were actually going to get to write before Java 1. Because we wanted to do things like we wanted to have a clean UI and code split. We wanted to do headless unit testing of a JavaFX application. It's quite a novel goal, but if you've got a proper domain model, then you could see how you could do that. And then we started to think, okay, well, it's almost like you could script this thing. It's almost like, what you need is some sort of interpreter loop like you might find in a video game. Wouldn't that be interesting? How could we do that? What could we do then? Well, we could have multiple implementations of the source of memory operations. We could have random ones. We could have ones which read from files. We could do all sorts of things. So then we started to put the interpreter model in. And then, of course, not only do we want to teach about the Java memory model and about the way that GC works, we also want to showcase some JavaFX features, and we want to learn, we want to have some fun at the same time. Yeah. And then, as this is being developed in the open as an open source project, the code should be clean and relatively well documented. I'll leave you to decide for what you think as to how well we achieved on some of these goals when you've read the code. Okay. So let's hand over to Jim. He's going to walk us through some examples from the code itself.
Thanks, Ben. So we started out with this probably around 6 months ago, and in the last 2 years, I've been working a lot with Flex. So I'm going to walk you through some of the complexities and some of the bits and pieces that we did. And if you haven't used JavaFX before, these next few slides will give you a good starting point into how you can just go and try and develop one of these applications. So let's talk a bit about FXML. It's very similar to how Flex skins work in terms of an iteration on top of that. And just to walk you through some of the syntax that you see here, we've got basically a VBox, which is just a layout that will just give you a vertical pane that you can then put things inside. And you also have things like HBox, which is then you can line things up horizontally. So you get this VBox and HBox kind of make a very flexible layout system that you can then add components into. And this is really where we start to see our first improvement on writing Swing UIs. You effectively here can start to break down the layout into something that can then be generated by, say something like a scene builder. So this kind of thing is usually it's not written by humans, it's generated. So this is the first nice thing that we get. So in this example, I've highlighted some things in bold. And what we can see here is we have a controller that's attached to this. So what will happen is as we start to interact with this separated model and view and controller, as you interact with things on the view, it's going to call back to the controller. What we have also is these IDs, and these IDs become quite important when we look at what's actually in the controller itself. You'll also see some things like label and combo box. If you're not familiar with UI controls, it's worth just having a quick look over the APIs. All these things are very similar in all different languages. So what about those IDs? Well, in our controller class, we can actually use annotations. And we had a text field and a combo box in the last slide, which would be where it's laid out on the screen. What this will actually represent now is what is that inside your controller? This is actually how you tell your controller that, okay, here is your text field. So if you want to see what text is in the text field, you have a reference to that. At the start of the application, this will all be bound together. We also have, you can also do this on methods. So for example, at the bottom of the slide here, there's a begin button. And what happens is when you click on begin, this is the FXML line, you call the begin simulation, which would then call back into your controller and then execute that method. And that's what this kind of on action hash begin simulation is. Now, if you think about that in comparison to Swing, when you're actually writing that stuff and setting it all up, you would have to have quite a lot of event handlers and dispatchers and capturing events in your controller. So this is a really nice way of getting these things connected together. So how is the FXML invoked? Well, the starting point of any JavaFX application is going to be your main class, which extends application. And there's certain things that you can override in that class, which then get you up and running. And the main one is start. So effectively what you're doing here, and there's some JavaFX terminology that I'll introduce you to if you're not familiar, is you set a root, which is then the parent, which is where everything's going to be contained in. So at this point, what I'm doing is I'm saying, take that FXML file, which I showed you at the beginning, and use the loader to sort of make that into the root. You also have, the analogy is kind of like to going and seeing a play. So what you're going to do is you're going to set the scene here at this point. So the scene takes the root, and you can imagine this as being effectively the scene that you're going to show in your application. And your application is kind of the stage. So you can move scenes in and out depending on what you're doing, and that becomes important when you're doing things like you're dynamically switching through different scenes, maybe on like a tab bar at the top. One important thing here is as well, is that all things in JavaFX are skinnable. So you actually have a massive CSS option to make custom components, and we'll go into custom components a bit more later. But you can actually define this in your CSS. This becomes quite important if you want to do stuff like white labeling, so basically giving your product to different companies. It means that you can actually apply different styles and different sizes depending on who's going to pick that up in the company. It also means you can style things differently depending on what platform you're on as well. So things may be skinned differently on Mac OS to Windows. What we do then is we set the scene, we set a title, and then we're ready to go. So there's one drawback that I see with this at the moment, and just to skip back slightly, is this is all really cool in terms of you have your memory controller and you have private fields, so it all hooks this together. But it makes testing this quite difficult because you effectively got things that are private variables that get bound at runtime. So my question, which I'm trying to find out this week, is how can we make controllers more testable, and how can we maybe start to mock some of these stuff so you can really start to test the functionality that's in the controller. So that's my mini project. The other thing that I say about a controller, which I missed, is you implement initializable. And what this does is, at the beginning when your controller starts up, you could set the initial properties on some of the objects, some of the components. So for example, what you might want to do is put hello in the text box, and you can set this from here, or you might have a default selection on the combo box. So this is our custom component. As Ben was saying and showed on the Flash demo, we have this concept of a memory block. We also have a concept of a memory block view. And the reason for this is keeping the actual model that Ben's going to show, where we're allocating stuff to the actual underlying model, and the view separate. And that's really important when it comes to keeping really nice, clean, and maintainable code. So our custom component here, memory block view, extends a stack pane. And the reason for this is we just take something that already exists inside JavaFX and build on top of it. So what we have here is that we have a rectangle, and we have a text property on top of it. And also we have then here the memory status. So as you saw from the demo, the memory can be in different states depending on what's going on. It can either be free, it can be currently allocated, or it can be dead. So what we do here is, if you'll see that this has got an object property wrapped around the memory status. This is our first introduction to bindings, and it's also a way of getting around having to fire events manually for when things change and update and reflect it in the UI, which is what you would have to do, as far as I'm aware, in Swing. So this is a recognition of the change without having a whole array of listeners and anonymous inner classes. And let's just go through how we use the bindings here in the constructor. So when we initialize one of these memory block views, we set it up with some styles. So we actually use the style property, which is on the rectangle itself, and then we do some bindings. So what we actually do is we use the static methods on bindings to say, well, when the memory status is equal to 3, then apply this FX fill style of gray. When it's allocated, set that to green. And when it's dead, let's set it to dark red. So what will actually happen here is as we interact with the model that's hooked into this, those states will be reflected without us having to go and do anything about it. So just a bit more on the constructor. Obviously, if you're extending something in the JavaFX API, or anything for that matter, you need to call a super, otherwise you're going to get some really crazy things happening. On the box, we then made it so it wasn't just a rectangle, we applied some more styles. So I guess the other thing to note here is where we were doing CSS styles before, you can actually also call these methods directly in code. So you, as well as you having this FXML way of representing things, you can also build this stuff up from scratch. You can declare a scene, and you can add things to it programmatically using add children. We then, for the first time, set up our text, and then we get the children, which is a call to the superclass, and we add the box and the text onto the stack. So where are we now? So I've gone through a few things. We have some blocks that can change, and we have some states that could be set on the block. So this is a very early screenshot of what we started to build here. The controller again, how do we, I guess the thing is now, so we've discussed having the memory block view and the memory block. How do we link those things together? So we actually do that inside the controller using a small method that we've got here called initialize memory view. And you can imagine this is, in effect, allocating to like a 2D array. You basically need to go across the width and the height and basically set each of the individual items. So what we're doing here is we're getting a memory block view from the pool and adding it into the grid pane. So again, going back to what we're seeing here, we're using a lot of the stuff that's inside JavaFX just out of the box. So these memory block views are actually set up in grid panes. So another important thing is background threading. And we've got two different varieties of this in the application. The first one is what actually controls the allocation threads. Basically, this is on an executive service, and I'll let Ben go into more detail with that as we walk through the code in NetBeans to discuss how that works with relevance to how we allocate memory in Java. We also have one other cool thing, which is the platform run later. And this is the JavaFX way of dealing with animations or transitions. So what I found was when I started writing the code and putting all this nice stuff in where we were updating and allocating memory was very quickly things started to freeze up, and there was a lag in things being flipped around and all these fancy animations that we tried. And I realized that I committed a cardinal schoolboy error of trying to run all these transitions on the UI thread. So platform.runLater provides you a queue in which you could just say, run this when you have some free resource. And usually it's pretty quick because it's just stacking up those animations one after another. So to do that, we just put our transition onto a runnable, and then we just run the transitions as it goes through. So in this example, this is just a small mechanism of fading out the block that you have here. So let's jump into the wilds of the code. I'll hand you back over to Ben to walk through how that works.
Okay, thanks, Jim. Right. So let's start off with the main classes. How's the code looking for people? Is that full screen? Is that readable? Yeah. Okay. Well, first of all, should we see it in action? Yeah. So it's kind of similar to before. This is actually with one of the random interpreters in place. It's the same idea as before. As you can see in the background, actually it's actually trying to get new T-labs and actually performing young collections. So we'll step through the actual model and the way it works. One of the problems that we have with this, we need some more interpreters, because these don't actually model the way that memory actually gets allocated, because all it's doing is it's actually killing off at a slightly slower rate than it's allocating. Actually, more things need to die young. But, hey, that's the beauty of the way that this has been designed, is that we can actually fix some things. And then I think this one will probably give us an out-of-memory exception finally. There we go. Okay, those are out-of-memories. Cool. Okay, so yeah. So let's take a look at that, the code in some more detail. Okay, so this was the slightly tweaked version of the main class, which the only thing we've done is we've also implemented a stop method. And basically, in order to have a good shutdown hook on the controller, basically you use this trick of actually getting the controller back from the loader and then calling halt simulation on it. And then the halt simulation shutdowns the thread pool. So this is the main controller block. And from that, when we actually run the application, you see there's a two-phase thing. First of all, we set up the values that we want for the different memory sizes. Let's put them back down to 3. And then kicking off the begin button activates the grid panes. So the grid panes are basically added dynamically after you've chosen what values you want for them. And then from this, basically it's been factored out. So there's a height constant which we need to change at some point. Basically, the idea is that when we get some more cycles, we'll make it so that the height of the simulation is also variable. And then that way you can schedule more allocating threads. So here's the calls to the initialized memory view that we showed in the slides. Yeah, and now here are the allocating threads. So basically the way that these work is like this. These are basically implement callable, because what's going to happen to them, if I come back to the controller, is that they're going to get submitted to an executor service. So the executor service is just a standard Java util concurrent. It's nothing special to JavaFX. It's just a standard Java util concurrent thread pool. And essentially, in the current case, I've only got 2 allocating threads, but we're going to carry on working on the application to add in the ability to have more different kinds of threads with different kinds of interpreters. So let's show you what an interpreter looks like. Okay, so inside here you can see I'm importing a couple of classes. Importing this class called opcode. And these are basically the basic operations that we might want to perform on our memory model. We might want to do nothing. We might want to allocate a block. We might want to perform a large allocation. Now, a large allocation would be one which went straight into tenured. That's not actually implemented yet, but there's flexibility in the model to do that as well. Or we might want to have some blocks die off. Okay, and so like any good opcode, the instruction may come with a parameter. So there may be a parameter which tells you which block to kill off. That's typically the use case for that. And you also have an ID, which is the thread ID. Because if I come into the memory model, this too is runnable. Okay, so basically, when we wrote this to be multi-threaded, I mean, it worked great in single-threaded mode, but actually when we tried to generalize it into writing a good multi-threaded version of this, it was actually very difficult. And what we found was that there were huge visibility problems, actually trying to make sure that actions taken by one allocating thread were visible on the UI and to the other threads was actually very, very difficult. If the allocating threads had true visibility of the model object. So that proved to be a very difficult concurrency problem to solve. So instead of which, we decided we would cheat. When faced with bad concurrency problems, cheating is usually the way to go. So what we actually do, let's find a bit of code, is we have this thing called BQ. And BQ is basically a blocking queue of memory instructions. So what happens is each interpreter interprets its file or does whatever it's going to do in order to generate the next instruction. And then it places them on a queue which go down to the model object. And then, of course, the model object itself now has to be runnable, and it actually runs in its own thread, and it just basically reads off the queue. So if you're familiar with other languages like Scala or Clojure, this is actually quite a similar idea. Essentially, rather than trying to have a reference to the model object and directly manipulate it, you're actually passing instructions over to it, which it's going to handle a bit like an actor would. Okay, so that's quite a neat pattern for doing that. And then that way, there's never any visibility problem because the things which the model is holding, namely the memory pools, are never visible to other threads. So that means that the model of memory that we have is always held completely consistent. So in most cases, we don't really have to do any synchronized. Okay, so let's look at the big run method from the model object. And this is also how we're able to simulate this and to do testing of this outside of the JavaFX part, is because we've got this model object, which is separate from everything else. So what do? Well, we pull an instruction off the queue. There's just a big while loop here with a switch statement. And as you can see, I've got an is shutdown flag, which will be a volatile boolean, which indicates that we want the thing to shut down. And so this is just basically a standard interpreter pattern for handling instructions which come in. And then basically for an allocation, I call the allocate method, and for a kill, I call destroy. So let's have a look at those. So basically allocate, I call it with a thread ID. It says this thread wants to allocate a block. So I've actually got a memory block which I'm calling from a factory. So inside here we've got a volatile sequence number, which is basically used to get a new block. There's a couple of helper constructors in there as well. So I've got this one which is get free block as well as a get block. And so this is actually the only bit of code where I need to worry about threading particularly. I just have to make sure that it's not possible for two threads to end up with the same block. So the rest of the block is very simple. It just denotes the ID, the overall allocation ID of the block, the generation it belongs to, whether I've touched it. So when I'm doing mark and sweep, which I'll show you the code for in a minute, we actually do go through and actually touch some things. And we have the memory block view. So there's a reference between the memory block and memory block view and the memory status. So let's look at the memory block view code. Yeah, and then this actually has a back reference because both of these objects need to be able to communicate with each other for when they die. Yeah. Here are the bindings that Jim was just showing you earlier. And yeah, all of this is really very, very simple stuff. So have a look at the code for that. Let's come back out to the memory block. So yeah, so we're allocating. So at this point we've got a nice memory block. It's not attached to a view at any point. So we add it to our allocation list, which is the global list of all the objects that the JVM has. And this is an exact model of the way that the JVM does it. It has a global allocation list of every object that it's ever allocated. And it uses that to walk through when deciding what to sweep. Bit lower down, bit of JavaFX stuff here. In order to actually trigger proper bindable behavior, there's get value and a get method, and it's really not clear from documentation, but you always need to use get value if you're going to actually have the binding work properly. If you use get, it just won't trigger bindings. From that, we walk through, we find the first. So basically, what this loop is saying is this is walk current TLAB. So for this thread, it walks along its current TLAB and see if it hits the end of the, see if it can find a free block. If it can't, if it finds a free block, great. It allocates this memory block it's just created to that thread. And if it can't, well, now we allocate a new TLAB. And then if we manage to get the new TLAB, that's great. We know that the offset 0 is empty, so we put the block there and then return from this method. Okay. Alternatively, if I can't get a new TLAB, that must mean that Eden's full. So if Eden's full, I'd better collect it. And then at this point, if Eden is reset, let's come into the young collection. So we get some log lists saying, just trying to do a young collection. So we've got a thing called evacuees. And basically, but the uncollectors are all evacuating. So what that means is that they're going to step through the memory pools, they're going to find any live objects, and then they're going to move them somewhere else. So the space which gets left behind is always totally blank. And that's modeled by this local variable evacuees here. Step through that. If we ever find an allocated one, we mark it to say, I've seen you, and I pop you into the evacuees list. The reason why this marking business is here is because it didn't quite get it working, but the aim is to also have the uncollectors run in parallel. So that at the moment, everything is single-threaded because the model reads events one at a time off the queue. But in practice, in the real garbage collection that the JVM does, actually it stops all the application threads and the collectors run in parallel. In this model, it's slightly different at the moment because events are still building up on the queue. So the marking is really there for dealing with multi-threaded passes of garbage collection, which are coming soon. Okay, and at the end of the pass, we've got a bunch of evacuees, and we send them off to survivor space. And once we've done that, we reset Eden to free space. We reset all the T-labs because we've got this thing which we call thread to current T-lab. So that basically your thread ID maps against a row in the grid pane. And then once you reach the end of the T-lab and you need a new one, you get the next one that's free. And that's how we handle the T-labs. And so this is how the resetting of the T-labs works. So you get your thread as your int value of the T-num, and then you just put... So the zero thread starts off with the zeroth row of the grid pane. The first starts off with the first, etc. And then at this point, you have to walk the entire allocation list for everything which is not null and unmark it. Okay, and this again is supposed to model the equivalent phase of GC. Okay, so we just tried to move stuff to survivor space, and at this point, we then have to check we've actually got space to put things in. And if that's not the case, because this check here is probably needs explaining, but if the number of evacuees we've got is bigger than the size of one of the survivor spaces, that means we won't all fit in survivor spaces and we've got to push stuff into tenured. So if we do that, then either we just shove everything to tenured, but we just check to make sure that we don't have to compact the tenured space first. So let me just show you, because this is a lot easier to see on the actual demo. So basically, we're allocating objects. Objects are dying. Everything's fine. Did our first young collection. Stuff's dying. No big deal. Bunch of stuff ended up in tenured. But notice it was only the generation 2 objects. So this is an example of what we call premature promotion. So objects are supposed to reach a count of 4 before they actually make it into the final into the tenured space. But if there's a lot of pressure coming from Eden space, like there is in this example, then it can actually be the case that objects are promoted before they make it. Now at this point, it's going to compact the tenured generation. Yeah, and there was just enough space in there to make everything fit. Okay, so the tenured space, the old generation, has to be compacted if it runs out of size. Okay, and then whether we've had to compact tenured or not, at this point everything should be fine. And let me show you. So these are how we deal with the memory pools themselves. Each memory pool has got a factory. And we can try, basically we have very simple methods to add a block to a memory pool, to return a value, to reset. And then tenured has this additional, tenured is like a special subclass of memory pool, and it has this way of trying to compact. Yeah, there's some detail about how the premature promotion works. So effectively, if we find ourselves down here, this means that we need to promote. So this constant is the tenuring threshold, and that's normally 4. If you play with the garbage collection subsystem flags to any degree, something weird happens and that number jumps to 15. And that's not very well documented, so when you're actually doing this with a real garbage collector, that's one of the things you just need to know. And then basically, you will only move stuff if they're actually full. But then, for the premature promotion, you can find yourself having to move entire generations of objects up just because there's no space in what's left behind. And this is how we do that. Yeah, some of this code does need to be slightly better documented, so please send me pull requests. Yeah, and a lot of this is actually very, very similar to the way that the garbage collector actually works. The algorithm is not precisely the same because we're dealing with a simplified situation, because we don't have to do a complete walk of all the object trees. None of these blocks refer to each other. Each one is just a freestanding block. Oh, let's do a little more on the interpreters. So, one of the things I have in here are a bunch of test cases. So here's an example of a completely deterministic iMemory interpreter. Basically, it's very straightforward. Once you've triggered it, all it does is on the 5th and the 3rd of every 5 blocks, it issues a kill instruction, and otherwise it issues an alloc. So out of every 5 blocks that you get 3 live ones out of every 5. So here's a random one. Basically, depending on its particular probability, it just calls math random, and then allocates you either. It does something slightly sneakier, because what you always want to make sure is you're allocating slightly more than you're leaving behind. So it sets itself up so that the sequence is either allocation, or allocation kill, and exactly which sequence you get depends on just some random numbers. And if we flip back to the controller, we can see how that works. So my typical value here is 0.2. Where did random go? Yeah. So if I run this now, we should end up with a situation where we're allocating only about half as many excess blocks. So that should lead to a few more collections before it actually turns out. Actually, let's write that down some more. Let's play with this. So the other thing that I really want to do is I want to extend this to actually deal with real garbage collection logs. I want it to actually basically take in a garbage collection log and output a stream of instructions that can be run through the simulator. I still haven't quite figured out how we're going to do that yet, but it's one of the next priorities for the project. Yeah, you can see that it's going to take a lot longer to actually run out of memory. All these examples will have actually eventually always run out of memory, but this one should now take a lot longer because it's now killing a lot more. Does anyone have questions about the code? Other areas people want to see? Do you want to see some more of the test cases? Yeah? Oh, I like this one. So these are all just actual general regular JUnit tests. There's nothing special or magical about them. We just use the countdown latch to land on a particular starting point. set up an executor service. We provide these sets of strings. And these are passed into the class that's called the memory interpreter file loader. And this is just a very, very simple parser, which basically, so it works like this. Essentially, there's the whole of the parsing is taken care of inside of this enum. So I've got the opcode types and the way that I've set up their constructors. Hang on. Are an output, and then basically you construct the token, compile the pattern inside that, and just checks to see whether it matches. So that basically allows us to do all of the file parsing for the simple interpreter format in just like 20 lines of code. And then that means that we can have test cases like this, which say a bunch of allocs, have a bunch of kills, have a bunch of kills. Shows you all this stuff, completely multi-threaded. Wait till the thread pools are shut down, and still pass the assertion. Okay, I think we're about out of time. Questions?
At the back.
A couple of questions. One, I noticed that your custom node, which you created for the tech stack pane with a red hat or a text node, you could just use a label.
Sure, yeah.
So a label you can style the background off, so it can basically be a rectangle. So you can give it a fill, you can give it a stroke, and it already has text. So it's an alternative way of doing that. The other thing I noticed was in the spot, when you've got your view block, are you jumping the FX thread or touching the C graph?
For memory block view. Whereabouts?
So just anywhere you touch any C graph object, it should be on the FX thread. So who's manipulating this? It seems like your memory allocator was manipulating your state, which is kind of directly round out to your view function. But at no point did you jump off the memory thread off the FX thread.
Okay, so this would be in the allocation. So
basically, when you're setting your value, so you're setting to get value set value on observable properties to round up to the view. When you touch those observable properties, you need to go to the FX thread.
yes, that's true, but we don't actually touch them from here. So basically, if you the get value, that just returns the value of the stack frame. Yeah, and from that point on, we call set block. Yeah. Oh, I see. You mean here? Because it's the actual observable property is this thing, is the memory status. So okay. So basically, you're saying that this line needs to be called from the FX thread rather than the.
Yeah.
Yes, that's probably a bug.
Yeah, it's notable that you somehow had your background thread doing all this work next up to your UI without the jump between the two threads. It probably caused you some interesting things.
Haven't noticed any so far, but it probably is worth having a better investigation of that line of code.
There's no thread protection, so it's just dark.
Yeah.
But so also, I was very curious of your get versus get value, because that should really be exactly what should be noted. The only difference between calling get value or set value is one should be the object version of it, and one is the. So it's like a double with a lowercase b versus a double capital.
Yeah, that may have been obscuring this behaviour. I mean, or rather, this line of code here may have been obscuring that behaviour because it just there was nothing about it why it shouldn't be working. And it was just trial and error, and it was just like right, the get value works.
We have a bug where it just happens to be dark because of threading the line that works.
Sure.
Sorry,
No, that's fine. I mean, patches are always welcome.
One thing I would be interested in is just finding out where we use the platform.runLater, because kind of based on your point that we're doing stuff on the background thread, I'm pretty sure that by using platform.runLater to sort of hive off some of this animation, is that possible without being on the FX thread?
Yeah, so basically platform.runLater is your way of getting from your background thread into the FX thread.
Right, so we do use that. I'm not sure where.
So any object that's part of your live scene graph that's connected to a scene that's visible has to be touched from the FX thread. So at any point you touch any of those objects, you have to do a platform.runLater.
Okay. So I think what we're doing here, or at least the logic behind it, is we update the binding and then we run the transition on the background, on the FX thread, on the runLater.
So you might be fine that the binding might turn out to be. So if the binding is not actually touching C cross stuff, then the binding is running 100% clean to your background thread. And it's only at the point where you do the animation you actually need to. But I thought your binding was setting star classes.
It is for most of it, but there are places where it's actually doing more than that. Okay, so I have a question. So is there a method handles interface to platform.runLater?
I don't know.
If there isn't, we should talk about that.
But yeah, you just got to be careful. It's the same as swing or any other UI toolkit, that anything that's actually visible is single threaded, so it needs to be handled in the FX thread. And generally, so we do throw exceptions if you try to add or remove nodes from the C graph from a different thread, but we don't check in any other places, just because we've got too expensive to do checks. So we kind of want to have it so it's always checked to make sure that the right thread is getting the warnings you need immediately going on. But it just gets expensive to do that, unfortunately, that thread check every time.
Okay. Any other questions? Anybody want to send me a pull request? Okay. Thanks, guys.